Given a charged conducting sphere, how do you think the charge is arranged inside it? A. All the charge is at the center. B. It's evenly distributed throughout the volume of the sphere. Or C. It's distributed only on the surface of the sphere. Pick your answer and I will tell you the correct one, along with the explanation, later in this video. First, how do we charge conducting objects? In our previous video, we discussed charging insulators by rubbing. So, why can't we do the same thing for conductors? Well, this doesn't work because conductors allow electric charges to move freely through them. When you rub a conductor, any excess charge that might be created will quickly spread out and move to other parts of the conductor or even to the ground, making it difficult to build up a noticeable charge. However, conductors can be charged by conduction or induction. Let us look at induction first. If you bring a negatively charged insulating rod close to a conducting sphere, the electric field of the rod repels free electrons inside the conductor, causing them to accumulate on one side of the sphere. This leaves a net positive charge on the side closer to the rod. These are called induced charges. When the rod is removed, the electrons rearrange themselves, neutralizing the positive charge. To obtain a permanent induced charge, earth the sphere momentarily. This is achieved by simply touching it briefly or connecting it to the ground. This causes electrons to flow out of the sphere. Once you remove the earth, you can also remove the charged rod, and the sphere will retain a permanent positive induced charge. Induced charge always has an opposite polarity to the inducing charge. To discharge the sphere, simply earth it again, in the absence of the rod. The positive charge will draw electrons from the earth, neutralizing the positive charge. This occurs in an instant. To charge a conductor by conduction, you simply need to bring it into contact with another charged conductor. Electron transfer will occur from the more negative body to the more positive one, and when the bodies then get separated, they now both have some charge on them. Charging by conduction produces the same polarity as that of the charging body. Now let us look at how charge is distributed in conductors. Consider a charged solid conducting sphere. In the beginning of the video, I suggested that charge had to be distributed in one of these three ways. Let us investigate them using Gauss's law. Before we look at the first possibility, you need to know that no electric field exists inside a conducting body with static charge on it. This is because free electrons inside the conductor will always move around until they neutralize the electric field. Now, let us use Gauss's law to go through all the possibilities. For option A, let us introduce a Gaussian surface inside the sphere. Knowing that the electric field in a conductor is always zero, it is clear that charge enclosed by the Gaussian surface must also be zero. Thus, charge is not at the center. By the same logic, the charge cannot be uniformly distributed throughout the volume of the sphere, because then Gauss's law will not be obeyed for any Gaussian surface within the volume of the sphere. This leaves option C. For this arrangement, any Gaussian surface will predict a zero electric field inside the volume of the conductor, which is correct. So, for any conducting material, static charge is only found on the surface of the conductor and not on the inside. This is true even for hollow conductors, and there is no charge on the inner walls. For both spheres, anything you do on the outside, like introducing an electric field or charging the sphere, does not affect the inside of the sphere. Also, since there is no electric field inside a conductor, its volume is equipotential. Outside, the electric field behaves as you would expect from any charged body. For a hollow sphere, with a charge placed inside, what is the charge distribution on it? Well, the charge inside has an electric field which induces a charge of the opposite polarity on the inner surface of the sphere, and as the electrons migrate to the inner wall, they leave a positive charge of equal magnitude on the outer surface. If you add these charges up, the net charge is still equal to the charge placed inside, and the electric field outside the sphere is similar to that of a charged solid sphere. Moving the charge around inside the sphere affects the charge on the inner surface, but does not influence the charge distribution outside. This is due to the fact that no electric field exists within the conductor, so the influence of the charge on the inside does not reach the outside. So, in general, a conductor acts as a shield for electrostatic fields, meaning that whatever you do with charges outside does not affect the inside, and vice versa. Such shields are often called Faraday cages. These cages can even block low-frequency radio waves. So, if you take a radio into a metallic cage, it might lose its reception. How is charge distributed at different points of an irregularly shaped conductor? Static charge is highly concentrated at very sharp points. In other words, there is a greater charge density at sharp points than at blunt ones. From Gauss's law, it then follows that sharp points also produce a stronger electric field than blunt ones. When a conductor is being charged up, it reaches a breakdown point where the electric field generated near its surface reaches 3 million volts per meter. At this value, it ionizes the air, causing it to become conducting and thus slowly leaks charge away from the conductor. This typically occurs at sharp points on the conductors since they always have a higher electric field than the rest of the conductor. If you liked the video, please leave a comment, like, share, and subscribe. That's it for now. Thank you for watching.